Hello and welcome to the live stream here at OKellyChemistry.com. I'm Ivana O'Kelly and thanks for joining me. In this live stream we're going to cover valence shell electron pair repulsion theory. So if you do have any questions during the live stream, I encourage you to go ahead and enter them into the chat. Ladies and gentlemen, let's get started. So the first question I have for us is, what is a bonded pair of electrons versus a lone pair of electrons? So a bonded pair of electrons are going to be electrons, a pair of them, that are shared between atoms within a molecule. So that refers to it being intramolecular. And second, a lone pair is going to be a pair of electrons that are not involved in bonding. And in VSEPR theory, we'll be focusing on the lone pair of electrons on our central atom. Another thing we have to look at is comparing the difference between electron domain geometry and the molecular geometry. So our electron domain geometry is predicted by two things. It's predicted by the bonded pair of electrons and the lone pairs that are found on the central atom. Versus our molecular geometry, it's based only on the bonded electron pairs around the central atom. So in the first part of this live stream, we're going to focus on electron domains where we have up to 4 different electron domains. So I have a couple of examples to get us started here. So the first one on the left here is a molecule of methane, CH4. So if we focus on our central atom, how many electron domains surround the carbon? So if I start here, this would represent 1. This would represent a second electron domain. This would represent a third. And this would represent a 4th electron domain. Notice that they're all single bonds. Moving to our second circle here, I have 2 diatomics. I have oxygen on top and I have nitrogen here on the bottom. So look at the domain that exists between the 2 oxygen atoms. Even though it is a double bond, it represents 1 electron domain. With our nitrogen molecule, it's a triple bond that holds the nitrogen atoms together, but this still classifies as 1 electron domain. Moving over to our last circle here, I have a diagram for a molecule of water. And let's count out the different electron domains here. So with our hydrogens, they will represent the first 2. And then on our central atom, we have 2 lone pairs of electrons. So this first pair of electrons would be number 3, and this would represent 4. So water actually has 4 domains of electrons that are found around the central atom of oxygen. So here is a molecule of carbon dioxide. So up on the left-hand side, I have the steps that we use to draw a molecule of carbon dioxide. Remember, our least electronegative element is going to go in the center. So that means our 2 oxygens are either side. And we're going to go ahead and fill in our lone pair of electrons on our outer atoms. So right now, each of these atoms has 8 electrons. Therefore, they satisfy the octet rule. So it is chemically stable. Now looking here on the left, here is a molecule of carbon dioxide. So we see carbon is in the center and we have 2 oxygens either side of our carbon. So filling out our chart here on the right hand side, the total number of groups of electrons that surround the central atom will be 2. The electron domain geometry is linear. The bond angle will be 180 degrees. The number of bonding pairs are going to be representative of either side of our carbon, so we see that there are 2. So even though they are double bonds, each double bond is a representative of 1 electron domain. On our central atom of carbon, we have 0 lone pairs. So when we have 0 lone pairs on our central atom, our molecular geometry is going to be the same. So let's move on to an electron domain where we're going to have 3 domains surrounding our central atom. So if we were to draw out, this is our nitrate ion. Nitrogen is in the center. and we have 3 oxygen atoms, we see that we have 4 pairs of electrons that are being shared between our nitrogens and our oxygens. So we'll put our oxygens here. It means that we're going to have a double bond. This is also a polyatomic ion, so it has to have a square bracket with a negative charge. Looking at column D here, we see that we have 16 unbonded pairs of electrons. Right now, our nitrogen is good. We see that it has 4 pairs of electrons, so it's chemically stable. So filling in our unbonded electrons, we're going to have 6 on the oxygens that only have a single bond, and this oxygen atom here on the left already has 4, so we'll fill in those 2. So now if we were to look at a model of the nitrate ion, we see that our nitrogen is in the center, we have our oxygens on the outside, and remember that this one is going to be a double bond. So filling in our chart, we see that we have 3 groups of electrons that surround the central atom. Our electron domain geometry will be represented as trigonal planar. Our bond angle will be 120 degrees. So if you take 360 and divide it by 3, that's where you get your 120. The number of bonding pairs will be 3. We have 0 lone pairs, so therefore our molecular geometry is going to be the same as our electron domain geometry. So here I have SO2, so sulfur dioxide. So sulfur is going to be in the center. I'm going to have 2 oxygen atoms either side. And I'm also going to have a lone pair on my sulfur. So filling in my unbonded electrons, this one on the left is going to have 6. And this is also an example of resonance because this double bond here could also be found on the left-hand side. So let's have a look at a model of sulfur dioxide. So here we see we have our sulfur in the center, we have our 2 oxygens either side, and we have a lone pair on the sulfur, which is our central atom. And that's going to be important because that's going to not only affect the bond angle, but it's also going to affect our molecular geometry. So the total number of groups that surround the central atom are 2 oxygens and 1 lone pair. So that means that we have 3 regions around our central atom, giving us a trigonal planar electron domain geometry. Our bond angle is going to be less than 120 degrees because this pair of electrons that are not bound to an atom are going to force those oxygens to become closer together. So again, the angle is between the oxygen atoms. Our bonding pairs will be 2. Our lone pairs on our central atom will be 1. So that means our molecular geometry will be referred to as bent or angular. So here I have CH4, known as methane. So carbon is going to be in the center. We see that we have 4 hydrogens on the outside. So 1, 2, and I'm going to draw it in its perspective diagram. So I'm going to have 4 hydrogens. And we know that hydrogen only needs 2 electrons to be stable. So let's look at a model of methane. So our carbon is in the center, and we have our 4 hydrogens on the outside. So you have 1 coming towards you, 1 moving away, 1 moving up. So the total number of groups that surround our central atom will be 4. Our electron domain will be referred to as tetrahedral. Our bond angle will be specifically 109.5 degrees. Our bonding pairs are 4. The lone pairs on our central atom are 0. So therefore, our molecular geometry will be the same as our electron domain geometry. So let's have a look at NH3. So here NH3 is nitrogen trihydride, also known as ammonia. Nitrogen will be in the center. Hydrogens are always on the outside. There's going to be a lone pair on top of nitrogen. So looking at a model of hydrogen, of ammonia. So take a moment there to look and see how the atoms are arranged outside the nitrogen with the lone pair on top. And if we fill out our number of groups that surround our nitrogen, we have the 3 hydrogens and the lone pair. Therefore, we have 4, giving us a domain, electron domain geometry of tetrahedral. Our bond angle here will be less than 109.5 degrees. Our bonding pairs will be 3. Our lone pairs will be 1. Therefore, our molecular geometry is not going to be the same as our electron domain geometry, and it will be referred to as trigonal pyramidal. So an easy way to remember that is that the 3 hydrogens are forming a pyramid underneath our nitrogen atom. And again, that lone pair is causing a repulsion, and it's forcing those hydrogen atoms further away from itself. Because remember, like pairs will repel one another. So then that takes us to H2O, which is water, dihydrogen monoxide. So our oxygen will be in the center. We're going to have 2 lone pairs. So looking at our model of water, put up here on my turntable. So we see that we have our 2 hydrogen atoms, they're coming around here, and we have our 2 sets of lone pairs. So let's go ahead and fill out our chart here. So we have 4 groups. Our electron domain geometry will be tetrahedral, again tetra meaning 4. Our bond angle, specifically for water, you need to know it, is 104.5 degrees. Our bonding pairs will be 2. Our lone pairs on our central atom will be 2. And our molecular geometry is going to be different because of those lone pairs. And the name given to that is that it is referred to as bent. So let's do a recap over these types of molecules. So specifically looking up as far as 4 electron domains. So if a molecule is shaped linear, it's going to have 2 bonding pairs and 0 lone pairs. Again, we're focusing on the central atom. Trigonal planar will have 3 bonding and 0 lone pairs. Angular is going to have 2 bonding and 1 lone pair. Tetrahedral will have 4 bonding and 0 lone pairs. Trigonal pyramidal will be 3 and 1. And bent will be 2 bonding and 2 lone pairs. So here's a summary chart for these molecules where we have up to 4 electron domains surrounding our central atom. So looking at linear, our example was carbon dioxide. Trigonal planar will be our nitrate ion. A molecule that was bent, or we also refer to that as angular, will be sulfur dioxide. For tetrahedral, we had methane, CH4. For trigonal pyramidal, we had ammonia, NH3. And for our bent, we had H2O, which is water. So now we're going to move into the second part of this live stream, where we're going to focus on electron domains that have 5 or 6 different electron domains. Again, we're focusing around our central atom. So the first one we want to look at is PCl5. So this time I'm going to bring up PCl5. So taking a moment to look at it and figure out the angles. So we can see that we're going to have different angles in this molecule. So our phosphorus is in the center, and we have 5 groups that surround the central atom. Our electron domain geometry, when we have 5 that surround the central atom, is trigonal bipyramidal. Our bond angle, we have actually 2 bond angles here. We have 90 degrees and we have 120 degrees. So taking a moment, we see here, this would be a 90 degrees, and between these two here, we would have 120 degrees. The lone pairs are 0, and the molecular geometry, because there are 0 lone pairs, you guessed it, is going to be the same as your electron domain geometry. So it will be trigonal bipyramidal. So next I have SF4. So with SF4, I'll put up here on my turntable for you. We see on our central atom, we have 4 fluorines and we have 1 lone pair. So the total number of groups will be 5. Our electron domain geometry is trigonal bipyramidal. Our bond angle here is also 90 and 120 degrees. Our bonding pairs will be 4. Our lone pairs will be 1. So therefore our molecular geometry will be different than our electron domain geometry, and we refer to this as a seesaw. So let me show you here how it can move from side to side, representative of a seesaw. So next up I have ClF3. So in this situation we're going to have, here it comes, we're going to have 5 regions around our central atom that contain electrons. Therefore the electron domain is going to be trigonal bipyramidal. Our bond angle will be 90 and 120 degrees. Our bonding pairs are 3. Our lone pairs are 2. And the molecular geometry, waiting for it to come around, it's like a letter of the alphabet. So it's a capital T. So we refer to that as T-shaped. Kind of cool. Next up is XEF2. So this would represent a model of xenon difluoride. So the total groups are 5. We see that we have 2 bonded and we have 3 lone pairs. So our electron domain geometry is still trigonal bipyramidal. Our bond angle, looking at where our fluorines are, we see they're in a straight line, so we're going to have 180 degrees. And then between our lone pairs and our fluorine, we're going to have 90 degrees. Our bonding pairs are 2. Our lone pairs are 3. Therefore, our molecular geometry is not going to be the same. But again, focus on the fluorines in relation to each other. That can help you identify the molecular geometry. So it's going to be linear. So next up, I have sulfur hexafluoride. So this is what it's going to look like. Our sulfur is in the center. We have 4 atoms of fluorine on the outside. So we have a total of 6 groups of electrons that surround our central atom. Our electron domain geometry is octahedral. So if I hold this up here, you should be able to see that the angle at which the outer atoms are forming an octahedron shape. So that 4 in the center connected to either side is going to make it like an octahedron. Our bond angle will be 90 degrees. The bonding pairs will be 6. The lone pairs on our central atom will be 0. Therefore, our molecular geometry will be the same. So it will be octahedral. Next, I have bromine pentafluoride. Get my lone pairs on here for you guys. There it is. So the total number of groups, we have 5 of our fluorines and we have 1 lone pair. So the total number of groups will be 6. So therefore the electron domain is octahedral. Our bond angle will be 90 degrees. The number of bonding pairs will be 5. Our lone pairs will be 1. And our molecular geometry will be square pyramidal. And here we have xenon tetrafluoride. So with xenon tetrafluoride, I'll put a model up here for you. So looking at it this way, we see that all of our hydrogen, our fluorine atoms are in the same plane. So that's going to help us remember our molecular geometry. So the total number of groups are 6. The electron domain geometry will be octahedral. Our bond angle is 90 degrees. Our bonding pairs will be 4. The lone pairs will be 2. And our molecular geometry will be square planar. So here I have a summary of the electron domains for 5 and 6. So if it's trigonal bipyramidal, the first one here, we're going to have 5 bonding and 0 lone pairs. For the seesaw, we're going to have 4 bonding and 1 lone pair. For T-shaped, we'll have 3 bonding and we'll have 2 lone pairs. For linear, we're going to have 2 bonding and we're going to have 3 lone pairs. For octahedral, we'll have 6 bonding and 0 lone pairs. Square pyramidal, we'll have 5 bonding and we'll have 1 lone pair. For square planar, we're going to have 4 bonding and 2 lone pairs. So here's a summary chart talking us through the total number of electron domains surrounding the central atom, then our electron pair geometry, the approximate bond angles, followed by our bonding pairs, and then our lone pairs again on our central atom. And then we have its molecular geometry name, and see if we can remember our examples that we did this evening. So first, for trigonal bipyramidal was PCl5, our seesaw was SF4, T-shaped was ClF3, linear is XeF2, octahedral was SF6, square pyramidal was BrF5, and lastly we had our square planar where we had 4 bonding pairs and 2 lone pairs giving us a square planar, and our example was XeF4. So ladies and gents, I hope you feel more confident now with VSEPR that if you were given a model of one of these or you had a picture of one of these, that you would be able to identify an example of them. If they came up on multiple choice questions, that you'll be able to identify bonding pair versus lone pair, and from that you'll be able to figure out the molecular geometry. So I'm going to hang out here. If anybody has any questions, go ahead and enter them into the chat. If you're watching this video, I'll see you next time.